I'm now going to look at the naming rules for a totally different set of compounds, and I'm going to call these the binary molecular compounds. The term binary is sometimes left out, but the word binary means two, so that's why I want to leave it in this definition here. And so what we're looking at are compounds that have exactly two different nonmetals in the formula. That doesn't mean there's exactly two atoms. Like, for example, water is a binary molecular compound. It only has hydrogen and oxygen in it, even though there's two hydrogens and one oxygen atom. So, two different elements that are nonmetals. Now, the big difference between these compounds and the ionic compounds is that they can form many, many different ratios when they combine. With ionic compounds, the ratios were dictated by the fact that you had to have the charges add up to 0. So they had to cancel. These nonmetals aren't going to have charge in the same sense, so that rule does not apply. So look at nitrogen and oxygen. Here are just a few of the compounds that they make. So NO, NO2, N2O, and they can't all just be called nitrogen oxide. They're distinct compounds with distinct properties. And so we have to come up with a name for each of these. So the naming is actually somewhat similar to what we did with the ionic compounds, but with one addition to that, and that is that we add prefixes in front of the names of the elements to tell us how many of each element is in the formula. And we still change the ending of the second element to "ide." So it's the first syllable plus IDE in most cases. You need to memorize the first 6 prefixes for this system, and I would imagine that many of these are already familiar to you, like mono meaning one, or di is two, tri like triangle, penta like pentagon, or hexa like hexagon. So you'll want to memorize at least 1 through 6 and 10, deca, just like decimal. So, how would we name this compound here? So we say the prefix and then the name of the element, so disulfur, and then 3 oxygens would be trioxide, not trioxygen. Remember, we changed the ending of the second element to IDE. Now, unfortunately, that's one of the only ones where the naming rules work perfectly without making any changes. So there are some very minor exceptions that we need to take into account. The prefix mono is only allowed to go in front of the second element. So if there's no number after the first element, that's a 1, in other words, don't use mono. We know that you mean 1. It's just understood. So mono can only go in front of the second element in the formula. So this compound, which should be very familiar to you, is called carbon dioxide, not monocarbon dioxide. By not putting a prefix on the element, we know that it's mono. So then what is the name of this compound? Well, there's 1 sulfur, and since it's the first element, it's just sulfur. And then 3 oxygens would be trioxide. So the name is sulfur trioxide. And then a rather minor one. Many of the prefixes ended in A or O, like mono, penta, tetra, but not di or tri. And it sounds awkward to have an A in front of an O, or an O in front of another O. And this is really only going to be the case with oxygen. So we ultimately are going to drop the A or the O if it's in front of oxygen. So this would right here be carbon monoxide. So it's not monoxide or monoxide or anything like that. We just don't want those double O's there. This compound here should be called diphosphorus pentoxide. although pentaoxide would still be acceptable. It's the double O's that we like to avoid. I don't know who decided that that's something that really bothered them so much they needed a rule for it, but they did. And so there we have it. There are some compounds where we use what we call a common name instead of following the naming rules that I just discussed. And the two of these that are most important are H2O, which is always called water. No one calls it dihydrogen monoxide. And NH3, which is always called ammonia, never nitrogen trihydride. And then there are plenty of other ones, all of which contain hydrogen, which you do not need to know. When hydrogen does appear first in the formula, we don't use prefixes at all, and we just name the compound without them. So there will be ultimately as many hydrogens bonded to the nonmetal as you need to get a complete octet. So it's almost like an ionic compound in that there's only a fixed ratio for each of these combinations. So for example, sulfur has 6 valence electrons. It needs to get 2 more, and it's going to get exactly 2 hydrogens to accomplish that. And so the name of this compound would be hydrogen sulfide, not dihydrogen sulfide, although technically that might be acceptable. HCl is named hydrogen chloride, not hydrogen monochloride. So now that we've discussed the naming of some of these compounds, let's talk about the forces that hold them together, and that is called covalent bonding. Instead of there being an exchange of electrons from a metal to a nonmetal, like we saw with ionic compounds, with covalent bonding we see a sharing of electrons between two atoms. Sometimes that sharing is very equal, and sometimes it's not quite equal. So we find this between nonmetal atoms primarily, and those are the only types of compounds that we're going to worry about where we find covalent bonds. So we still follow the octet rule here, and we do it in a slightly modified way. The atoms share enough electrons with each other so that they have 8 valence electrons, and shared electrons count towards that total. So in a way, the electrons are being double counted. Each atom looks at the electrons around it and wants 8. Hydrogen is the big exception. Hydrogen still follows the duet rule, and it only wants 2 electrons. That's very important. Hydrogen does not want an octet. Covalent bonds are strong, but they are not generally as strong as ionic bonds. Many of the bonds which make up your body and any other living organisms are going to be covalent bonds. Bone is going to have more ionic bonds. But you can think about this. You're not, basically liquefying into a puddle because the bonds that you have are so weak. No, they're strong, just not as strong as ionic bonds. So think about this for a second. If you try to heat salt with a very, very high flame, and I don't necessarily recommend doing this, but if you were to take salt and put it in a pan on an oven and try to heat it, the salt won't melt. The sugar, on the other hand, when you put it at a high enough heat, it will certainly start to melt, and it will start to smell very unpleasant. So here's a very simple example of how a covalent bond might form. So we have a hydrogen atom and another hydrogen atom. Each of them has a single electron. Hydrogen wants a duet. So each hydrogen atom would like to think it has 2 electrons, so it can be like helium, the nearest noble gas. So they come together, and when I say come together, that means their nuclei approach closer, and then they share their 2 electrons mostly in between them. So these are the individual atoms, and this is a hydrogen molecule. So whenever we have covalent bonds holding atoms together, we are going to use the term molecule to describe them. It is not appropriate for ionic compounds, which we already saw, like with sodium chloride, makes up repeating unit cells or crystal lattices. So when we talk about water, an H2O molecule, that is a single entity. We can find a single water molecule, but there is no single sodium chloride molecule with only 2 atoms in it. So let's look at some typical covalent compounds. So water we've already seen. This formula is the formula of many carbohydrates, but glucose is probably the one that's most familiar. C6H6, which would be the compound benzene. Carbon dioxide. H2S we saw was hydrogen sulfide, sulfur trioxide, and many others. There are some elements which are always found as molecules rather than as separate atoms. And 7 of these are found as pairs of atoms. And we are going to call these the diatomic elements, or the elements which form diatomic molecules. And they're going to be needing to be memorized. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you look at the periodic table, you'll notice that with the exception of hydrogen, all of these elements touch each other and they form the shape of a 7. You might ask, well, what about the element underneath iodine, astatine? It very well might be diatomic, but the issue with that element is it is so exceedingly rare that we haven't really been able to make a study of it. There are other molecular elements out there. Phosphorus, for example, forms pyramids containing 4 phosphorus atoms, and sulfur forms crowns containing 8 sulfur atoms. Carbon, as diamond, forms what are almost infinite networks of carbon atoms, and it can also form layers in graphite. But we don't need to worry about those other kinds right now. I just want you to focus on these 7, and the reason for that is because they will come up a lot in the chemical reactions we will talk about. Before we get too far into the shapes of these molecules, I need to introduce one more concept, and that is electronegativity. Remember earlier that we talked about periodic properties, and we said that moving one way on a periodic table causes an increase in some property. Specifically, we did that for atomic radius. We said that as you move down the periodic table, the radius increases, and as you move from left to right on the periodic table, the radius decreases. Electronegativity is another trend that works like that. So the definition of electronegativity is it tells us how strong that element's attraction for electrons is. And specifically, it's how strong its attraction is for the bonding electrons, the electrons that are bonded to it. The greater that the atom's electronegativity is, the more it pulls the electrons toward it, and we could say the less it wants to share. So, as I mentioned, it's a periodic property, so we can determine it based on its position in the periodic table. So electronegativity increases up a group and going from left to right across a period. So that means ultimately the elements with the greatest electronegativities appear in the upper right of the periodic table. The exception to that is going to be the noble gases. The noble gases have no electronegativity. So that leaves fluorine in the upper right-hand corner because it's not a noble gas. It is the most electronegative atom by far. And a general rule is to say that the closer an element is to fluorine, the more electronegative it is. So here we have the most important examples of electronegativity. They're scored on a 4.0 scale, with fluorine being the most electronegative at 4.0. And what we are mostly going to be interested in is the differences between these numbers. So in a moment I'll be saying, well, what's the difference between carbon and fluorine? Well, carbon is 2.5, fluorine is 4.0. That difference is 1.5. So it's the differences in the electronegativities that make a difference. You do not need to memorize all these values. However, it would be very useful for the coming discussion if you at least made a note or wrote down the electronegativities of fluorine, oxygen, nitrogen, carbon, boron, and hydrogen. And those aren't too hard, because if you know fluorine is 4.0, you just subtract 0.5 each time you move left. So 4.0, 3.5, 3.0, 2.5, hydrogen over there is 2.1, and then boron, which we're not going to talk really about, is 2.0. Chlorine, it wouldn't hurt to know, it's 3.0. But these other elements, because they're metals, they have such low electronegativity that they're not going to be included in this discussion. I'm going to end this video here and keep it kind of short because the next couple topics take quite a bit more time. Thank you.